A little bit about Professor Rachel. If I can find your, where is your bio? Where did I put it? Well, a little bit. I think if people who are working in gallium nitride would know who is Professor Rachel Oliver. I'm talking to a few friends here, and when I said to them, we are going to have a talk by Professor Oliver, they said, "Ooh, they are very excited to hear these talks, and hopefully they'll be coming in." But I guess we go straight to the talk then. Rachel,
Sure.
is it okay?
Yeah, that's fine.
So the floor is yours.
Excellent. Right. Let me see if I can make the technology work. So you'll see yourself for a second, and then I'll switch it. There we go. Okay, can you see my slides?
It's coming up slowly. Okay. It worked for me. I can see it now.
Excellent. And everyone can hear me, yeah? Then I shall get started. Okay. So, hi everyone, I'm Rachel. I am speaking to you from a fairly dark Cambridge currently. It's fairly early in the morning here. And I work at the Cambridge Centre for Gallium Nitride, and I'm going to talk to you today about the materials science of light-emitting diodes. Now, when I say to people I'm a materials scientist, they find that fairly confusing. And I wonder whether quite a lot of the people listening are electrical engineers or physicists, and they may be less familiar with material science. So what is a materials scientist? Well, a lot of the time when I do say to people I'm a materials scientist, they say, "Oh, textiles, that's a nice career for a girl." Or they assume that I work in fashion, for example. Actually, I have the greatest respect for my colleagues who work in textile science, but that doesn't encompass all of what materials science is. Now, sometimes when some people say to me, "Oh, what is a materials scientist?" I explain what it is by referring to an older discipline, which is metallurgy, because originally that's what materials science stemmed from, metallurgy, the study of metals, and it's then broadened out into other exciting technological materials. I think it took a little while for people to figure out we really needed to understand the science of materials beyond metals, but materials science now spans a much broader range. Nonetheless, it has its roots in metallurgy. So my picture in the background there was of a big reel of copper, and early metallurgists might have been interested in studying copper for its mechanical properties. So just let me get a pointer up. So they might take data like this, where they measure the stress applied to a material and see how much it stretches. And that kind of behavior, the elastic and plastic behavior of a metal, is controlled very much by the structure of the defects inside it. So these defects are what we call dislocations. Now, what I've got here is kind of a schematic of a crystal, and you can see these nice ordered lines of atoms. In fact, this is a 2D schematic of a three-dimensional situation. So you can think of these as planes of atoms, sheets of atoms which run into the page. And then at some point, rather than the sheets of atoms being beautiful and continuous, they start to be bent. And then here, there's a sheet of atom that just ends in the crystal rather than continuing on. That extra sheet of atoms, I would call it an extra half plane of atoms, is what's distorting the bonding around it. And the edge of that extra sheet of atoms would run into my slide, into the page, creating a line through the crystal where the bonding is disturbed and distorted. And that is a line defect that we refer to as a dislocation. You can see those lines here, indeed in copper, in a transmission electron microscopy image. And these defects in copper and in other metals now are really quite well understood. So that doesn't sound like what electrical engineers or physicists might have come to a talk to listen to. Why am I talking about defects in a metal? And why would a materials scientist care about LEDs at all? Well, I will show you in a little while why it was important to me to explain those defects. But before we talk about the material science of LEDs, light-emitting diodes, it's worth me saying that in fact all of us should care about light-emitting diodes because this is a huge energy-saving technology. In fact, about 20% of the electricity generated globally is used for lighting. That's a really large percentage of the electricity we all use. And light-emitting diodes compared to conventional incandescent light bulbs are enormously more efficient. So by switching to LEDs, we can cut down the production of CO2 and other greenhouse gases really very, very substantially. And amongst the concerns about the climate, these LEDs are a really important technology. So if we look at an LED light bulb, what's actually inside it? Well, this is a sort of standard LED light bulb as you might buy it from the shop. And if you remove this white diffuser, inside you find this kind of yellow ping pong ball, it looks like, but it isn't just a table tennis ball. It's actually a phosphorescent material, a material that absorbs one color of light and gives out light of another color. And if we take off that cap, underneath it, we've got the actual LEDs. There are, let me see, about 5 or 6 on this particular printed circuit board. And with the LEDs on, we can see that the bulb gives white light, but underneath that phosphor cap, we can see the LEDs themselves emit blue light. And the blue light is absorbed by the phosphor, and some of it is re-emitted as yellow light. So we have this transition from blue to yellow, and the blue and yellow light combine to give at least the appearance of white. And in more sophisticated bulbs, the phosphor might give out also red and green light to give a more complete white hue. So we've got inside the bulb, and now we're going to drill down inside the light-emitting diode itself. So this is what we see if we chop into a light-emitting diode and look at it in the scanning electron microscope. A layer of semiconductor material with contacts made to it, and in there is a p-type layer and an n-type layer. And to see more detail, we can zoom in further here using the transmission electron microscope. So now we've got our p-type gallium nitride, and our n-type gallium nitride would be at the bottom down here. And in between, the most important set of layers in the LED will be these ones here labeled as MQW, multiple quantum wells. I'll zoom right in on those. So this is the real light emitting part of the light emitting diode, consisting in this commercial LED that we've sectioned here of layers of indium gallium nitride, about 2 to 3 nanometers thick, separated by slightly thicker layers of gallium nitride. And that's where this talk is going to focus, on these quantum wells and their structure and properties, their materials science. So what is the link between the copper with the dislocations controlling its mechanical properties, which I mentioned at the beginning, and these light-emitting diodes? Well, the link is in these defects, these dislocations that I mentioned. Here I'm showing a transmission electron microscopy image of a piece of gallium nitride. We're seeing it in atomic resolution, and the bright dots are the gallium atomic columns. So this image just shows up the gallium atoms, essentially. And in this region of the gallium nitride, there is indeed one of these defects, these dislocations. Now, if I were feeling interactive, I would ask you to spot it, but that's actually a really difficult job in a picture like this. So I'll draw on some lines showing where the atomic planes go. And we can see that just like in my schematic, there is this missing half plane of atoms, and the other atomic planes deviate around that. And in this region here, where we have the dislocation core, we have the missing half plane running into the page through the crystal, away from us as we look at it. And that is exactly the same kind of defect we talked about in the copper. If we zoom in on it in a bit more detail, you can take detailed images of the dislocation core. This is an actual image. The second one is a simulation of that image based on this structure here. And what we can see is that where the end of that missing half plane terminates, we have not the normal structure of 6-membered rings of atoms, but instead we have 5 and 7-membered rings of atoms. And that hopefully. And that shows us how this dislocation distorts and alters the local bonding within the structure. Now, this is a simpler LED. This is one of the early LEDs grown at Cambridge. Still has the same key features, P-type and N-type gallium nitride, and quantum wells in between. It's a very, very simple LED. And we're now imaging it from the side. The previous image would have been looking down from the top. And we can see these lines running through it. And these are the actual lines of the dislocations. I said we were looking at a line end on. Now we're looking at the same lines from the side. And we can see that they penetrate all the way through the device. The reason they're present is that we're growing our gallium nitride on a substrate which is a different material, in this case sapphire, and that leads to stresses and strains which lead to the generation of dislocations. And then those dislocations thread, we say they're threading dislocations all the way up through the material, and they cross through the active region. Now, particularly in the early gallium nitride LEDs, even commercial devices had a number of dislocations, a density of dislocations per unit area of about a billion per centimeter squared. Now that's in contrast to materials like gallium arsenide, which are used for making infrared LEDs, and similarly the gallium arsenide, gallium phosphide family of materials, which are used for making red LEDs as well, where the dislocation densities would typically be round about 1,000 per centimeter squared or less. But actually both types of device work really well. They're both long-lived, have lifetimes in excess of 50,000 hours. But if we were to take our gallium arsenide and increase the density of defects by about a factor of 10, the lifetime of that gallium arsenide device would drop from maybe 100,000 hours down to less than 100 hours. And in fact, the gallium arsenide device might not really work at all. Gallium arsenide devices with a high density of defects very quickly become hot, and then the heat causes them to fail. And in the worst case, you would pretty much turn them on, wait for a second, and the whole device would go foot, and that would be it. So why is it that gallium nitride devices can survive a density of defects about a million times higher than the density of defects that we see in gallium arsenide devices as being critical, as being likely to ruin the device? Well, we were inside an LED before as a SEM image. Now I'll just draw a schematic and talk about what's happening to the carriers, the charge carriers, the electrons and holes in this material. So what we want in an LED is we have P-type gallium nitride and N-type gallium nitride, from which holes from the P-type gallium nitride, positive charges, and electrons, negative charges, are injected into this quantum well region. The quantum well region consists of thin indium gallium nitride layers sandwiched between these gallium nitride barriers, which have a wider band gap. So we have alternating regions of indium gallium nitride, which has a lower band gap, and gallium nitride, which has a higher band gap. And that makes these kind of pockets for electrons and holes to become trapped. And the electrons and holes are trapped, recombine with one another, and as the electron loses energy as it combines with the hole, that energy is given out as photons, light, with a wavelength which is characteristic essentially of the band gap of the indium gallium nitride. Now, the point of the quantum wells is to force the positive and negative charge carriers together into a really narrow region or really small volume of the material. That makes it much more likely they'll combine to give out light. It's like if one of you came to visit me in Cambridge, if I said, oh, come and meet me and we'll meet in Cambridge, the two of us could wander around for ages and never actually meet up. But if I said, come to the Department of Materials Science and meet me in the reception area, then we'd be in a much smaller volume. It's much more likely we'd be able to find one another. So that's what quantum wells do. They put the electrons and holes in a small volume together, make it more likely that they'll find one another and recombine, and light will be given out. That's the process that we want happening in our quantum wells. We want the electron and hole to recombine and light to be given out. What happens when we introduce a defect running through the material, one of these threading dislocations, these lines of mistake in the crystal that we saw in the transmission electron microscopy image? Well, the band gap of a material is very much a consequence of its periodicity. The defect breaks the periodicity, and therefore it essentially affects the band gap. It introduces states in the band gap, and those states are present both in the gallium nitride barriers and in the quantum wells, because the dislocation runs through both of them. And that means there are new routes for the electron and hole to recombine, which mean that heat is given out rather than light. That makes our device inefficient. And what we would expect to happen in a quantum well device is that if a dislocation is present, the electron and hole, although they are trapped by those energy differences in the direction across the quantum well, are able to move around within the plane of the quantum well. And that would mean that they could move within the plane of the quantum well and often find the defects and recombine. And if there are lots of defects, lots of dislocations, that becomes more likely. We get lots of heat out and the device doesn't work. That's essentially what we understand as the problem in gallium arsenide devices when they have a high density of defects. So the concept is that there must be something within the quantum wells which prevents the electrons and holes from diffusing within the plane of the quantum well, within this orange layer in my diagram, and reaching the dislocations. And the first candidate for what that might be was variations in the composition of the quantum well. So here, I'm drawing my quantum well as having like dark orange and light orange regions, which are meant to be higher and lower indium content. The high indium content, dark orange regions, we might expect to have a lower local band gap, electrons and holes that just happen to move to that region will be trapped in the high indium content, low band gap region. They won't be able to move smoothly in the plane of the quantum well. They won't be able to meet the dislocation. So when they recombine, they'll give out light, which is what we want. It's actually possible that rather than compositional variations, it could actually be thickness variations in the layer that is the quantum well that trap the electron and hole. That's because in very small structures, we saw these were in the LED, we saw in the TEM only about 2.5 nanometers thick. In those very small structures, the available energy levels are quantized depending on the thickness of the quantum well. And those quantization energies drop, and we have a lower energy state in the thick part rather than the thin part of the quantum well. So the thick bit can also act to trap the electron and hole, so they can't move around and get to the dislocation, and so that they tend to recombine to emit light rather than heat. So coming back to my original question, what is a materials scientist? Well, a materials scientist is somebody who looks at the structure of materials to see how it affects their properties. I'll come back to the other parts of this diagram in a second. And what we have now in what I've just talked about an LED is very much a materials science problem. What we want to know is what's going on with the structure of the quantum wells that means that the electrons and holes are trapped in some way and cannot diffuse around to get to the defects. So what is it about the structure of our quantum wells that allows the good property of efficient light emission that's robust to the presence of many defects? If I now come on to the rest of this tetrahedron, what we want to be able to do is identify those really good structures, change the way we make the material by the processing of the material to enhance, make more of those structures, or in other ways improve them, make even better properties, and all of that will give better performance for our light emitting diode. So In our current picture, we have a mystery as to why these devices really work well despite all these defects. If we understand what structure controls that, then we can use the structure, improve the structure, enhance the structure, and get better devices out. So these other elements, processing and performance, are also key parts of what materials scientists see as their role. Using processing to control structure and properties to get things to work better, whether that's a copper rod or an LED or a computer chip or a bridge or whatever else that we might want to make. This is the Meltons-Fleming tetrahedron of material science, and it's something that really kind of encompasses my discipline. So we've got a material science problem. We need to understand the structure of our LED, to understand its properties, and then to figure out how to process it to make it work better. Let's see how we might solve that problem. Well, back in 1997, people thought they had understood the structure of LEDs. This is a very well-known paper from Narakawa et al., in which they take images of quantum wells, and rather than the quantum wells looking perfect and uniform, they look sort of blotchy, blobby. And this is actually an image in which the contrast arises from strain, okay? But indium gallium nitride has a different lattice parameter, a different atomic spacing to gallium nitride. So where you have high indium content regions, you'd expect there to be more strain. And these, therefore, regions of high strain were interpreted as blobs of high indium content, which is this picture with these blobs of high indium content that could trap the electron and hole that we've already seen. And I think everyone was very excited and very satisfied that they'd understood what was going on with these LEDs, that the high indium content regions were protecting them, preventing carriers from diffusing to dislocations. And this really was like seen as the answer to the problem. And there were patents about how you would optimize these high indium content regions, which was people improving the processing of these devices to try and improve the performance. There was just a sort of problem with this though. I'm going to show you what it was. This image here, we have these grey bands, which are our quantum wells, okay? And this is another transmission electron microscopy image here at quite high resolution, so we can see individual lines, which are the atomic planes. I hope you can see that on your screens as well. And if I just switch to a different screen, here we go. Okay, so this image I just showed you is actually the first image in a sequence, a video, where we've kept the electron beam in the electron microscope on these quantum wells. Now you can see these quantum wells look maybe slightly blotchy in places, but basically fairly uniform. But if we expose them to the electron beam, as we expose them to the electron beam over time, they change. So that what we've got now this is actually couple of minutes exposure to the electron beam, we can see that now our quantum wells look all blotchy. I'll just play that one more time. So they start off fairly uniform, and over time, as we expose them to more and more electron beam irradiation, they become more and more blotchy, like the quantum wells I showed you in that Narakawa paper. So what we're seeing is that if we have a fresh sample in the electron microscope, it doesn't look like it has these clusters, or maybe very few of them. But the more we expose it to the electron beam, the more of them we appear. So it becomes a very difficult question. Are the clusters we see, the blotches we see in the images, the real structure of the LED? Or is the structure brought about by how we're imaging the LED? Well, I said material scientists were kind of descended from metallurgists. What would a metallurgist do in this situation? Well, one thing a metallurgist would do would be to look at the phase diagram to figure out whether the thermodynamics of the material is expected to lead to it being all broken up into these high indium content regions. This is an early phase diagram for gallium nitride and indium nitride. The composition of the material is along the x-axis and the temperature is along the y-axis. And underneath this solid line here, what we'd expect is to see the material splitting up into gallium nitride and indium nitride rich regions. And that would include at the temperature for growth of indium gallium nitride and LEDs. Where does the phase diagram come from? Well, we look at the Gibbs free energy versus composition curve. So now I've got a material I'm calling an AB alloy. And at high temperature I'm calling T1 here, that Gibbs free energy versus composition curve has just a single minimum. And in that case, we expect random mixing of the A and B atoms. But if I lower the temperature, the energy versus composition curve has this kind of W shape with two minima. And what that means is that if I talk about a composition X dashed, it can lower its energy by splitting up into regions of composition X1 and regions of composition X2, because X dash has a really high composition, but the other two compositions, which are lower and higher in B here than X dash, have much lower energies, and by having a bit of each, we can have a lower overall energy. Now, there's another line on this diagram, which is this dashed line. And the dashed line is defined not by these minima on the curve, but by these 2 points of inflection. Now, those points of inflection are important because if we're within the part of the curve defined by those points of inflection, then if we start off with material at X dashed and it just decomposes just a little bit into slightly more A-rich and slightly more B-rich material, we'll instantly lower the energy. That means that as soon as the decomposition starts, the energy gets lower, and that means that decomposition can happen really quickly. So fast decomposition occurs within this dashed line, which we call the spinode. Now, what we've calculated there is what I would call a chemical spinode, and that's what Ho and Stringfellow calculated in their paper. But if we introduce the concept of strain in our material and say that A and B have different lattice parameters, and therefore materials of different composition will be strained relative to one another, then that tends to suppress the spinode because of the formation of strain energy or equally of disordered interfaces on decomposition. We call that the coherent spinode. So we have to think now about the effect of strain on these materials. I've got two further phase diagrams, one from Karpov and one from Louis and Zunger, both of which try and express the impact of strain on this phase diagram. Now, they look quite different to one another. It depends exactly how you include the strain and what strains you think about. But if we compare them to the original Ho and Stringfellow phase diagram, we can see that they're not going to give the same predictions. My little blue LEDs here are representing roughly the temperature at which you grow indium gallium nitride in a standard commercial process in an LED. And what we can see is that the Ho and Stringfellow phase diagram does predict we split up into gallium nitride and indium nitride regions if we're at this composition and temperature relevant to LEDs, but the other two phase diagrams don't. They expect the material to stay as a random alloy. So the phase diagram analysis has at least shown us that there's a bit of a question here as to whether we'd expect this separation into gallium nitride and indium nitride rich regions and the formation of these indium rich clusters. So how would a metallurgist attack this problem experimentally? Well, they might use a technique called atom probe tomography. What we've got here is a needle-shaped sample where the apex of the needle is about 100 nanometers or so. And it's held at a very high voltage. And it's also at a low temperature. And we just use a little pulse of additional voltage superimposed on that high standing voltage. And that will take the material over the threshold for field evaporation. And because of the presence of the counter electrode, it's not worked. Try that again. Because of the presence of the counter electrode, the field will cause the atoms to fly off, I hope. Okay, this doesn't want to animate. The field will cause the atoms to fly off from the needle to this position-sensitive detector over here. And that will show us where the atoms land, which we can trace back via the radial symmetry of the field to where the atoms came from. Now, that will give us an XY position for these atoms. And we also have information about their Z position simply by their arrival time, because we can't have atoms from back here in the needle evaporating before atoms at the apex of the needle here. So that gives us the X, Y, and Z coordinate of each atom. And we can also work out what atoms they are, or what ions they are as they evaporate. And that's because a heavier ion will take longer to fly from the needle to the detector. So if we measure that time of flight, we can use it to do mass spectrometry and to find out what atoms we have present, all of which gives us X, Y, Z positions and atomic identities. It allows us to build up compositional maps in 3 dimensions. Now it's animated. Right, now I'm where I want to be next. Okay. So as done on metals, you would use it to build up pictures like this. Now, this is a material that has indeed split into 2 different regions of composition, 2 different phases. It's a steel, which also contains chromium and copper. And I'm showing up this separation here as isoconcentration surfaces, which means volumes of material where the surfaces join points of constant composition. And here we're just showing up the individual atoms just as dots. We're not showing all of them, we're just showing the chromium and the copper. You can see how we can use this technique to map out in 3 dimensions. These are 3-dimensional images, and they could be 3-dimensional videos when we had the data. We can map out the composition in 3D and find this nanoscale phase separation that we've been talking about. So how do we do this on semiconductors rather than metals? Well, with semiconductors, it turns out to be pretty difficult to get these very fast voltage pulses, which are used to cause field evaporation in the metals. The conductivity is just a bit low. So instead, we hold the sample at close to the threshold for field evaporation, and then we pulse a laser, which just warms it up a tiny bit, and that lowers the threshold of field evaporation, causes the ions to evaporate. And then we use the same type of analysis. We work out their X and Y and Z position from their arrival position on the detector and the order at which they arrive. And we use their time of flight to work out their atomic species. So what we wanted to do was do that to gallium nitride. Now, this was several years ago now, and this is something that's done fairly commonly on semiconductors at this stage. But at the point when we did it, no one was doing it on semiconductors. So the first thing we had to do was work out how to make a really sharp needle with our indium gallium nitride quantum wells at the top, because that sharp needle is what lets you get the high fields, which is what facilitates the whole atom probe technique. It needed to be on the end of a long spike, so about 100 nanometers at the apex, but about 2 microns high. And then it needed to be attached to our voltage source and with reasonable conductivity, all kind of connected together. And we had to figure out how to make that. And our starting point is a long way from being a needle. It's a flat sapphire wafer with a layer of N-type gallium nitride on top and the quantum wells above that, which, far from being a 100 nanometer apex, typical wafer is 50 millimeters or 2 inches across. And the way we decided to make this was using focused ion beam milling. So we have a beam of ions that we're going to use to either sputter away part of the sample surface, or we can also use it to deposit material. We introduce a metal organic precursor, which is decomposed by the energy of the ion beam, and then it's deposited on the surface. This FIB, or focused ion beam technique, is quite well known now. It's used for nanoscale prototyping, also for very commonly preparing transmission electron microscopy samples. And when we want to prepare a transmission electron microscopy sample, what we do is put a platinum layer over a region that we're interested in. So this is the deposition of material in the focused ion beam. And then we use the ion beam to dig 2 really big trenches either side of that metal strap. And we thin down to form a membrane. Now, that was something that was established before we started trying to do atom probe. So that's exactly what we did as a starting point for making our atom probe specimens. Here's one of our membranes from our quantum well wafer. And you can see we've also used the ion beam to cut down here and across, making this sort of gate structure, which is ready to take out of the wafer. We bring in a needle, and you can literally make sticking tape out of the available platinum in the FIB to tape your sample to the needle, and then we cut it out from the wafer and bring it away. In our early experiments, our sample holders were just steel wires, so we brought it to a steel wire, strapped it, taped it onto the steel wire with another band of platinum. We can remove the needle, and then we tape down all the way around with lots and lots of nice conductive platinum to make that electrical contact we need in order to be able to do the atom probe experiment. And then we start to mill in annually in kind of donut shapes that bring the radius of the pillar we initially had down to a post and then to an ever thinner needle. Then this is one of our very first working atom probe samples with our steel needle and this very, very thin spike of gallium nitride sticking up from it. And this is one of our early atom probe data sets. So what we can see here, this is again a two-dimensional render of a three-dimensional data set. It's indium gallium nitride quantum wells with gallium nitride barriers. I'm not showing the nitrogen at all. I'm showing all of the indium atoms as little tiny orange dots, and I'm showing 25% here of the gallium atoms as turquoise dots. But all we can really see is just these stripes of indium. It's not obvious whether there might be compositional variations within the indium gallium nitride. And that's partly because this is a projection through the whole of our 100 nanometer diameter needle-shaped specimen. So it's difficult to see any variations in composition because of how they superpose on one another. But it's also just not a good idea to analyze the composition of your material just by eyeballing it and going, oh, I think that might be a bit phase separated. Instead, we need to use a statistical analysis. So what we do is we chop the quantum well regions up into little volumes, and each volume contains 50 atoms. And then we measure the composition of each of those volumes, and we draw a histogram of how often a particular composition occurs against the compositions. Now, if the indium gallium nitride were not phase separated, if it were just a random alloy where whether you got an indium or a gallium on any particular site was just like the toss of a coin or the roll of a dice, then what we'd expect is a binomial distribution, which is this solid line here. And our actual observations with the composition of blue emitting quantum wells lie really very close to that line. We haven't got any evidence here looking at the graph of any form of splitting up into indium-rich and gallium-rich regions. If we look at a green emitting sample, it's not quite so perfectly lying on the line, but it's actually still very close to that expected distribution. And we'd always expect in a limited size data set a certain amount of noise around the prediction. In fact, for both of these, you can use a chi-squared test, and there's not good evidence that there's any reason to reject the null hypothesis, which here is that the indium gallium nitride is just a random alloy, that there are no big clusters of indium, that those structures, which we said would protect the LED against the harmful effects of defective dislocations, there's just no evidence that they even exist in this data set. That suggests that the TEM data that we've seen is to do with damage to the sample by the electron beam, not the material as it's found in an actual working LED. So that was a concept that we introduced into the nitride community, that these clusters of indium were not real, that they were just the impact of the electron beam. And as this was kind of like a big cornerstone of how people thought about the operation of these devices at the time, that was quite controversial. And a lot of people were just like, Rachel, you've got this new technique that nobody uses on semiconductors. It's something from metallurgy. You're probably just doing it wrong and you can't find the clusters because you're doing a bad experiment. So, we're just going to dismiss what you say. So we needed some clusters. We needed to have a sample which had some clusters so that we could prove we could detect the clusters. But we had a way of growing quantum wells which didn't appear to give clusters. So that was kind of difficult. So what we decided to do was take an atom probe specimen and put it in the TEM and hit it for really quite a long time with an electron beam to try and generate some clusters. And then we took a piece of the same sample and the sample that had been in the electron beam, and we looked at them both separately in the atom probe. Now, for our control sample, again, we've got data, which is the frequency at which different compositional regions occur, and it lies quite nicely on the line, which is the bimodal distribution. The data is the bars. And what I've done at the bottom is I've subtracted that prediction that binomial distribution from the data. And what we can see is it just looks like fairly random numbers, because you can't really say there's any tendency to deviate from the prediction in any particular fashion. But if we look here at the damaged sample, the one that's been hit with the electron beam, and we do that subtraction, we now see that there's too much material at low indium contents and too much at high indium contents, and not enough at the average indium content. And that is a classic signature of phase separated material. And also, if you do a chi-square test, the probability of this turning up randomly turns out to be less than 0.1%. So when the clusters are present, we can detect them using the atom probe. We then actually did manage to grow some quantum wells which contain clusters. We did it by growing the material not on the standard C plane of gallium nitride, which is like the top of this hexagonal prism if you represent the crystal structure of gallium nitride in this way, but on an orthogonal plane, the A plane, which is at 90 degrees to that C plane. And when we did that, you could actually see in the atom maps these kind of blobs of high indium content region. And I was like, oh, no, we don't do our analysis like this. It'll all turn out to be random when we look at it in the proper statistical analysis. So we looked at it in the proper statistical analysis. Here's a normal C-plane quantum well, and at the top, an A-plane quantum well. And again, these frequency difference plots. And what we're seeing is that, again, for the sample we could, with our eyes, see those clusters of indium, there is indeed a deviation from our expected kind of noisy frequency difference plot to something with much too much low indium content and high indium content material, and not enough of the kind of average indium content. So the atom probe can detect clusters in indium gallium nitride. So for our standard C-plane quantum wells, which is what we find in your standard LED, we can't find the clusters, and we're capable of doing so. So the easiest interpretation is they're not there. So we need something else that might be keeping these LEDs working. And we said at the beginning that there might be variations in the thickness of the quantum well. Well, if we go in and look at the quantum well with either the transmission electron microscope or the atom probe, we can actually find deviations in the thickness of the quantum well. In the atom probe here, we're using these isosurfaces, these surfaces which join up constant composition, to highlight the bottom interface and the top interface of the quantum well. Now, this lower interface is really quite smooth, but the top interface has quite a lot of roughness, 1 or 2 monolayer high islands. And if you look very carefully in the TEM, where projection problems make it more difficult to see them, you can just about pick out the same thing. Now, we've been working with theoretical collaborators to understand what impact those fluctuations in the thickness of the quantum well might have on the properties and how the carriers move. So this is an atomistic calculation. Every atom in the quantum well is simulated here. And where we have the red contrast, that's where the electron is likely to be. And where we have the green contrast, that's where the hole is likely to be. At the top, we're looking at the quantum well in cross-section, and at the bottom in plan view. And we have 3 configurations here of many that were calculated. And in each case, you can see that the electron tends to localize on this well width fluctuation, but the hole localizes at some other point, seemingly randomly. And it turns out that's just where you happen to have, by the random throw of the dice, a couple of indium atoms right next to one another. And that's enough in indium gallium nitride to trap a hole. You don't need a big blob of high indium content material. You just need a little bit of high indium content material. And that gives places where we trap both the electron and the hole. They now, because of those fluctuations, can't diffuse to the defects, which means the defects don't trouble gallium nitride LEDs anything like as much as you might expect. There's a whole other story here, though, because they're also, the electron and hole, separated spatially within the plane of the quantum well, which tends to make them recombine more slowly, which is actually a bit of a disadvantage of this natural phenomenon we're seeing. So we now know that the LEDs work not because of big blobs of high indium content material, but because of these naturally occurring compositional fluctuations that are just random, and also because of well work fluctuations. What's left to understand? Well, Many things, unfortunately. I'm just going to mention one of them before I finish. This is efficiency droop. This is how the efficiency of an LED varies with the current applied through the LED. And at sort of moderate currents, we get very, very high efficiencies in these devices. At very low currents, we see some non-radiative recombination at defects dominating, possibly at point defects here. But at very high currents, we see the efficiency dropping again, or very high current densities. And why this happens is quite a big controversy currently within the nitride community. It's been attributed to Auger recombination, to carrier leakage, and also to what we call density-assisted defect recombination, whether the carriers escape those localization centers at high carrier densities and the dislocations become an issue again. I'm going to show you here briefly an optical way of understanding whether the carriers are trapped. Essentially, if we look at the emission energy from a quantum well with temperature, for indium gallium nitride quantum wells, it shifts first to the red and then to the blue. Now, you expect shifts with temperature because the band gap changes with temperature, but here we've removed the dependence of the band gap on temperature. So this isn't to do with the band gap change. This is to do with where the carriers are sat in these different trapping sites, these different localization centers in the quantum well. At low temperatures, they will just be trapped wherever they happen to land in the first place. But if we warm them up, there will be a little bit of thermal energy available for the carriers to get to lower energy sites, and that gives us a redshift. And they tend to go to all the lowest energy sites at that point. But at even higher temperatures, there's just a bit of thermal distribution of the carriers amidst the available sites, and that gives us a blue shift. So this temperature dependence is a signature of carrier localization. And we see it at low powers or at low carrier densities, which is equivalent to low currents in the LED. But if we go up to much higher powers or much higher currents, this signature tends to vanish. Now, at low power, we have this expected redistribution of carriers amongst the localized states with temperature that I just mentioned. But what's going on at higher powers? Well, what we're hypothesizing is that all the available states are actually just filled with carriers, at which point you lose this signature of redistribution. But you also might expect there to be now no more trapping centers left if you add more carriers, at which point carriers may be able to diffuse to the defects and recombine non-radiatively, losing efficiency. So is this saturation of localized states a key thing in droop? Can the carriers now diffuse around the quantum well as if there were no localization centers and recombine non-radiatively at dislocations? Or are we actually talking about, for example, Auger recombination because of the high density of carriers leading to electron-hole recombination, giving not light, but the emission of electrons out of their bands? This is actually still a controversial issue, but the point I'd like to make is that without an understanding of the real structure and therefore of how the carriers are localized or move or become trapped within that structure, we can't really come up with meaningful predictions about any of these other phenomena. So we still need the material science to really understand what's going on. So I've been telling you about the material science of LEDs. I've told you that they contain, our nitride LEDs, many, many defects, and that we use the atom probe to show the structures which protect those LEDs from the impact of the defects. We think that the key structures are fluctuations in the width of the quantum well and random fluctuations in the indium content, not great big, huge indium clusters. And that is what enables the LED light bulbs, which are a very efficient lighting technology for our futures. And all of this, we've been understanding how the structure of the material relates to its properties, which will then allow us to improve how we process the devices and hopefully to get even better devices in the future or devices with new functionality. So that's it. Thank you very much for listening.
Fantastic. Thank you.
Now, I'll come out here for a minute so I can see you.
Yes, you open the floor to. There's one question, perhaps Aizat, if you're still here, if you want to ask the question yourself. Hello, Aizat.
Yes.
Yeah, if you want to ask your question yourself, go ahead.
Oh, I think my question is as stated.
Okay, just let me read the question.
Okay, thank you, Prof.
You're asking what is the effect of number of quantum well on the LED performance?
So the number of quantum wells is having a higher number of quantum wells is quite good in terms of distributing the carriers across the quantum wells. So from that point of view, if you have more quantum wells, you'll have a lower carrier density, which means you get less droop, which means that the device should perform better. Now that's kind of a really simple picture. It's possible that if you have too many quantum wells, you actually don't inject carriers into all of them. You only get particularly the holes in the ones near the P side. And then a lot of the quantum wells aren't actually doing anything. So at that point, then it doesn't really matter, but maybe you stick with a lower number of quantum wells. That, to a certain extent, is a kind of engineer's answer. If you answer the question as a material scientist, you can't just keep putting in more and more quantum wells because the material is strained, and the strain energy associated with the quantum well gets more the more wells you have. And at some point, that drives relaxation, which introduces extra defects, which makes the properties worse. So, in fact, you don't necessarily have kind of all degrees of freedom to have as many quantum wells as you like anyway. You have to worry about how that affects the strain energy of the system and whether you can still grow good material. The pragmatic answer is that different manufacturers seem to use between about 3 and 8 quantum wells, and all the devices work fairly well, but not brilliantly.
Meaning to say that currently they are just simply compromise the number of wells.
Yeah, I mean, I think it's always going to be a bit of a compromise because, as I say, the strain in the material is that means that you can't just design a device and grow anything you might want. I think, yeah, to the extent you can grow a thing, it's always a case of balancing the ability to inject charge carriers all the way across and the fact that ideally you might want more to reduce the carrier density. If we understood why droop was happening and could mitigate it in other ways, we might not have to worry about having more quantum wells to reduce the carrier density, however.
All right, good. There's another question from Yo-Yo. When we are talking about localization carrier in quantum wells, are you referring to potential minima in the Q wells or trap levels in the forbidden
When I
gap?
talk about localization centers, I'm talking about potential minima within the quantum wells. So essentially, I'm talking about either the indium content varying or the thickness varying, which means that the local band gap or the local quantization areas within the InGaN change. So these are desired localization centers. Well, probably desired localization centers that are going to prevent the carriers from diffusing to defects. There'll be additional sites in the bands within the forbidden gap which relate to the defects.
All right. Any more question from the audience? Well, basically the wells design. Yeah, you can design in any way you want. You know, the levels and everything, but the problem will be growing it, right?
Yeah, exactly.
So whatever design that you have, you get a good simulation results and whatnot, but
Yeah.
growing it.
So there's a lot of interesting designs for quantum wells grown with compositional gradients. So sort of either different quantum wells within the stack having different compositions, or one side of the quantum well across a 2.5 nanometer layer having a different composition to the other. And it's very, I won't say it's easy, but you can make lovely simulations which show potential profiles and say your device will perform like X, Y, or Z, but it's much more difficult to actually realize that. And for some of the subtler designs, like you're pushing the limits of some of the measurement techniques to know whether you actually have grown what you want at all, because a compositional profile that you measure in something like the transmission electron microscope will be blurred out by the size of the interaction volume between the electrons and the sample, and isn't necessarily a perfect rendition of that composition at all. And equally, there are limitations with the atom probe as well.
Correct. So just it's like designing on paper will be fantastic, but making it is either it doesn't
you have
work.
to feel sorry for the people who are trying to make it and then check whether they've made the right thing or not.
It's just like you either make it right, but you don't measure it correctly, so that you don't get. So you're saying you do TM and then it doesn't give you the right image, then you don't know whether your design.
So you might have made it, but you don't know.
Or you might have made it, but because of the image come out blurry, the measurement.
Not so sure.
All right. Maybe we can have another one question. That's one more. What will be the main difference between inorganic and organic LED in terms of illumination properties and the quantum world?
So the big thing about inorganic LEDs is that you can drive them harder than organic LEDs, even though they do droop, which basically means you get more light per area of LED. Now, it depends what you're trying to do. So if you're trying to light up a whole room, so you want a light bulb in your ceiling, you want a lot of light in what is actually a fairly compact device, and there inorganic tends to win. Where organic tends to win is more often things where you need like structure, so you want different pixels, and it can be easier in terms of the device processing in situations where it's not quite so important to get ultimate brightness, but you want to be able to produce things like big panel displays. Organic LEDs are more important in that context. So it very much depends on the application, whether what you care about is really high brightness or slightly cheaper and more processability, more manufacturability. There's another one as well.
Yeah, there's another one.
The efficiency of near UV LED is lower, mainly due to the quantum confinement efficiency from the lower barrier height from the quantum well and quantum barrier. Okay, there are lots of reasons efficiency of near UV LEDs is lower. So the quantum confinement efficiency is less. It's also, so it depends on your exact device, but quite often you're working with gallium nitride quantum wells and aluminium gallium nitride barriers. So there you have potentially less localization, which means the devices are more prone to being affected by the dislocations. Sometimes there are just more dislocations. There is an issue with the algan-GaN and the algan-algan devices with light extraction. So it can be that the light tends to, because of the specific band stretches, the light all tends to go sideways within the quantum well and not come up, and that makes them less efficient. And also the injection efficiencies are lower because the wider you make the band gap of the barrier materials, the less p-type conductivity you have, and then you haven't got very many carriers to put in. So with low indium content in GaN, I think probably the main effect there is to do with confinement efficiency, but I'm not sure. I'd have to, I'd have to look at the system specifically. But yeah, the wells there for low in GaN quantum wells, the wells are very shallow. So carrier escape is going to be a big issue in that case. You do in fact get quite a lot of carrier escape out of quantum wells, even in the blue and the green. One of our reasons for using multiple quantum wells that I didn't mention is that basically the carriers escape from one quantum well and then end up in another quantum well and recombine rather than being lost entirely. But with very, very shallow quantum wells, I think, the low barrier heights will be an issue.
Right. Any more, maybe? If not, then I think that is it.
Cool.
We have 1 hour.
We are perfectly to time.
Yes. So thank you very much again, Rachel, for waking up so early this morning, get ready. So Now it's 7 there, right?
Yeah, it's 7. So I will go and get my son up for school. He will be delighted. Okay.
Okay. But before we leave, just a customary, if everybody can switch on their cameras and we can have a sort of group photo. It's not really a group photo, but yeah. If I can get everybody, maybe Yasmin, when everybody's ready, can have a snap.
Yeah, sure.
Let me also change my layout so that I can get. Okay. Let's wait a few more. Be available. Okay. I only have what? 1, 2, 3, 4, 5, 6, but 10 in my view. I don't know how to change. Make it more. Oh, you can. I can have everybody here. Good. Okay. Min, dah dapat lah. Can you get the?
Just a moment.
Just a moment. Okay. So everybody, big smile.
Okay, 1, 2, 3. All right. Thank you very much, everyone.
Again, thank you very much, everybody, for joining.
Right, thank you, everybody. Lovely to
It's
speak to
very
you this morning.
grateful. Thank you, Rachel. Safe driving your son to school today and go back to work. Don't forget your bike.
I will
Don't
look
forget
at
the
today. Thank
All right.
you.
Thank you very much. Hope
Bye.
we can have another session like this in the future.
That'd be great.
And,
Thank you.
Maybe in Cambridge.
Yeah, that'd be good. If we can ever travel again.
Yes. All right. Again, bye-bye, everyone. Thank you very
Bye.
much. Have a nice day.